Now that we've defined entropy, we can state the second law of thermodynamics, which is that ds is greater than or equal to 0 for any system. The ds greater than 0 applies to spontaneous processes. And these will be irreversible processes. So things like our gases mixing, right? So our system will keep increasing in entropy until it reaches the case where ds is equal to 0, which is when we have reached equilibrium. Right? There's no further change in the entropy of the system, and this will also apply to a reversible process. Any reversible process will have ds is equal to 0, because in a reversible process you are essentially at equilibrium at every step along the way. So let's look at this in a little bit more detail with sort of a contrived example, but one that sort of illustrates what's happening in an isolated system. So if we have let's imagine we have an isolated system. This is an example from your textbook. So this wall I'm drawing around the outside here, this is our doer or whatever that is preventing any matter exchange. It's rigid. The volume can't change of this system. So this is an isolated system, which means, again, if we go back to our very, very beginning of our discussion of thermodynamics, in the first law, means that matter and energy cannot be exchanged outside of this. And inside of this system, we have a rigid wall. So rigid meaning that the volume of either left and right won't change. And we have two compartments that have fixed volumes, volume A and volume B. VA and VB are fixed, which means that for any process in here, dVA and dVB are equal to 0, just by how we've defined things. And we can say that each of these has a temperature, TA and TB, that are not necessarily equal to each other. And so this wall is rigid, but it can allow heat exchange. So we can see heat going back and forth between these. Now, because everything's rigid and no volume can change, we can say that dW for any, dW for A or B or any process we can come up with is equal to 0, because there's all the changes in volume are equal to 0. Okay, so that means we can write out the first law for each of these compartments. DUA is going to be equal to DWA, but that's equal to 0, plus DQA, and DUB is going to be the same thing, with 0 for the work component and DQB. Okay, but one thing we can know here, because this is an isolated system, energy can't be created or destroyed, so any change in the internal energy of A has to come from B, right? So A and B are directly related to each other. So we can say DUA is equal to minus DUB. This is just stating that energy is conserved. Okay, so now we've set up this system. Let's look at how, now that we have entropy defined, and let's imagine these are all reversible processes. I guess we don't have to define that for du and for du, so that we can apply entropy here, right? So if we have some sort of process, we can say DUA is equal to T dSA, because the entropy for side A is going to be equal to dQ reversible over T by definition, over TA, which means that we can say that dQ reversible is equal to TA, and that has a D in front of it, dSA. And this is a relationship we're going to see come up multiple times in this class. This relationship between reversible heat and ds is, just rewriting the definition of entropy here. And then dUB is equal to sorry, that needs an A there, TB times DSB. Okay, and then one other thing we can say, for any process that happens, the entropy change in the whole system is composed of the entropy changes in compartment A and compartment B. All right, we've got all this set up. So the overall entropy change in the system is dSA plus dSB, but we can rewrite those in terms of dUA over T, because if we just divide this equation here divided by TA, that gives us an expression for the entropy in terms of the internal energy, and dUB divided by TB. But we have this conservation of energy relationship up here, and so we can rewrite this. We know that dUA and dUB are opposite and equal to each other, so we can say that ds for the system is equal to, we'll pick B, dUB times 1 over TA minus 1 over TB minus 1 over TA. Okay, so we've got this expression for the entropy of the system. Now, one thing we know is that if TB is greater than TA, we're going to have energy, the energy is going to flow from B to A, right? We're going to lose energy from B. This is just based on personal experience, right? We know this. dUB will be less than 0 because energy is going to flow from B to A because the B is hotter than A. And what does that mean for the overall entropy of the system? Now, according to the second law, it should be positive. And right, there's no overall change in the energy for our entire system. So what is driving this? And it is the entropy change. So we should have an entropy that's greater than 0. All right, and so if TB is greater than TA, now looking at this expression here, we should get that ds is positive, right, if TB is greater than TA. Because, sorry, the whole expression is positive, because this will be negative, but this will also be negative, because 1 over TB will be smaller than 1 over TA because it's a larger number. And so overall ds is positive. All right, but what about if TA is greater than TB? What if we have the opposite? All right, well then dUB is greater than 0. Now our energy is going into B from A, and we'll have the exact opposite here. Both of these will be positive, and so we'll still have that the entropy change is positive. And so we can see for the spontaneous process that we know, just based on experience, that if one hotter than the other, energy is going to flow from the hotter to the colder substance. That is accompanied by an increase in the entropy. There's no net energy coming into the system, but it does lead to an increase in entropy, which is why that process is spontaneous. One way we can think about this is if we sort of chart over time the value of entropy for a system. Entropy will increase and increase and increase until it reaches a maximum, and that is what we call equilibrium, where there's no further increase in entropy. And these are all spontaneous processes that are driving the entropy higher. So this is a nice figure from your textbook that I think illustrates sort of this idea of the second law as entropy is always increasing in our system. And so that is, this is sort of a contrived example, but this is an example showing how a spontaneous process, just a temperature difference in this case, the flow of energy is accompanied by an increase in entropy, and that's what makes it spontaneous.